Okay, to finish off that last problem, so we found that we didn't have inflection points, but we do have to name the intervals of concave up and concave down. So up is going to be from negative infinity to negative 1, so that's here. And then it's also up from 1 to infinity. And then we also name concave down is this middle section from negative 1 to positive 1. So remember to answer both parts of that question are the possible inflection points. So you'll name the inflection points, and then you'll also name the intervals of concave up and concave down. Alright, so the next thing we're going to look at is the second derivative test for local extrema. And remember, extrema is just max and mins. So when it's saying this, it's saying if you test the first derivative equal to 0, and then the second derivative turns out less than 0, meaning negative, then it has a local max at that particular point C. If you take the first derivative equal to 0, that's where we find critical numbers, and then you take the second derivative and that becomes greater than 0, then you're going to have a local min at that particular point C. And then in some cases the test fails and it may or may not have a local max or min, or might not, or may have neither. So we're going to look at an example using this, and it'll say find all relative extrema. So the previous ones were find inflection points and find concave up or concave down. So this one says find extrema, so that's max or mins. Use a second derivative test when possible. So just like the other ones, the first thing we're going to do is, if you look above at that theorem, it uses the first derivative and the second derivative as well. So we'll just start off by finding derivatives. Our first derivative in this case is going to be 4x to the third divided by 4, so that'll reduce to just x to the third minus 4x. That's our first derivative. I'm just going to put our second derivative over here. Take the derivative of that one and it'll be just 3x squared minus 4. So on this one, what we want to do is find possible critical points. So which one of these do we go back to for critical points? Good, the first derivative. So you go to the first derivative for possible critical points. Remember, we set that equal to 0, so 0, I'm just going to write that. First derivative equal to 0. So I'm going to have 0 is equal to x to the third minus 4x, and here we factor out an x, and we'll have x squared minus 4. That's difference of squares. So x minus 2, x plus 2. And then set each one of those equal to 0, so x is equal to 0. Negative 2 is equal to x, and positive 2 is equal to x. And these are possible critical numbers, or critical points. And so for this second derivative test, we're actually going to plug our critical numbers in, possible critical numbers, into our second derivative. So our second derivative above is 3x squared minus 4. And so we're going to start with our first critical number, so we're just going to start with 0. Everywhere that there is an x, plug in 0. And that's going to give us just negative 4. And since that negative 4 is, let me get a different color, negative 4 is less than 0, it's a negative number, that means we have a max. And that's by our theorem above. So if it's up here, if it's less than 0, oops, thought that was a highlighter. If it's less than 0, it's a max. If it's greater than 0, and that just means if it's positive, we have a min. So this one's less than 0, so that's a max value. We're going to test the second derivative at all the critical numbers. So this time I'm going to test it at negative 2 and see what we get. So we'll have negative 2 plugged into that. Simplify it, and we get an 8. 8 is a positive number, and a positive number is greater than 0. Since it's greater than 0, by our theorem, we're going to have a minimum value there. And we're going to do one more. We're going to test the second derivative at our last critical number, which is positive 2 this time. Plug that in. You'll have 3. Positive 2 squared times 3 minus 4. That's also 8. 8 is positive, which positive just means greater than 0, so you have a min. So now what we want to do is name these max and mins as ordered pairs. So we know the x values of them. We know the x value of 0, negative 2, positive 2. You're going to have to plug those into the original function. So f at 0, f at negative 2, and f at positive 2 to find the y value for those functions. So let's start with 0. 0 to the 4th divided by 4 minus 2 times 0 squared plus 4, because we're going back into this original function up here. Right? Anytime you have x and you solve for y, you got to go back to the original function. So plug that in and we get 4. So 0, 4. Plug in negative 2 this time, so it's going to be negative 2 to the 4th divided by 4. Everywhere there's an x, plug in negative 2. Simplify that, you get 0, so the ordered pair is negative 2, 0. And we're going to do it one more time with positive 2. 2 to the 4th minus 2 times 2 squared times 2. And we get 0 again, so this one's positive 2, 0. So this 0, 4 was a max, negative 2 was a min, and positive 2 was a min, so we'll come back over here. 0, 4 is our max value. That's a maximum. This one ends up being a minimum, and this one's a minimum. So for these, it'll say find all relative extrema. Remember, extrema just means find the max and mins using the second derivative test. So in this case, we use our first derivative to find possible critical numbers, and we plug our critical numbers into our second derivative and just determine, is that value positive or negative? Is it less than 0, meaning negative, or is it greater than 0, meaning positive? And we use our theorem to declare if it's a max or a min. And so we'll look at one more. Let's come back over here, one that's kind of already done. And then you can also sketch that out if you wanted to. You can see right here where I just did, this is negative 2, 0, positive 2, 0, 0, 4. So a function may look something like this. That's a 4th degree, and you can kind of see how it applies. This next example, I'm just going to kind of walk you through it. It's similar to the one that we just did. So just like before, when I have the chance to algebraically FOIL this thing out to the side and distribute it, I'm going to choose to do that instead of work with product rule and then product with chain rule within product rule. So the easier thing to do here is if your original function is not FOILed out and factored out, you probably want to go ahead and do that first. So that's the scratch work to the side. Simplify it and then multiply it by x, and so we do all of that previous scratch work to get to this point. So all I did was keep rewriting and keep doing the algebra till I get there. Now, because I know I'm using the second derivative test, I did my first derivative, just pretty easy, and then I went ahead and calculated my second derivative as well. So it's a safe place to start on these kind of problems. So the first step is to find critical points or critical numbers And we do that by taking our first derivative equal to 0, or where our first derivative is undefined. In this case, we set it equal to 0, and we factor out a 12. And then afterwards, we factor this to x minus 3, x minus 1. And then we're left with possible critical points. And when we're using second derivative tests, we take possible critical points and plug it into the second derivative. And our second derivative is here. So that's what we're going to substitute our critical points in. And so my first one that we worked on was the critical point 3. So I take critical point 3, substitute it in my second derivative, and that value just became positive 24, and since that's greater than 0, by definition it's a minimum by theorem. Then I tested my second critical point in the second derivative, and I got a negative value, so that means it's less than 0, declares it's a max. Well, I only know my x values, so to find the y value of that, I have to plug it back into the original equation. So that's what I'm doing here. Take my 3, plug it back into the original function. I just came up to my very first original version of f of x, plugged it in, and got 0. So that's the ordered pair 3, 0. And then I did the same thing for the critical number 1, plugged it in, the original function up here, simplified, and I got 16. So the other ordered pair is 1, 16, and then I used my definitions to determine that 3, 0 is the min and 1, 16 is the max.